Welcome back, everyone. Here we're working through the group work in section 15.1, thinking about double integrals over rectangles. So the first one has us not just estimating, but actually exactly evaluating the double integral given over here. And so the idea here is that we can actually draw precisely the volume that we're talking about because our function is so clean, right? Our function is actually a constant. And so, what's the graph of our function going to look like? Oops. Right? It's horizontal, right? It's just a horizontal plane at z equals 3. Right, so there's the graph of our function. And what about our rectangle over here? X's from -2 to 2, y's from 1 to 6. So it's going to look something like this. And so here's our rectangle R. And indeed, looking at the volume bounded, we come up to our graph. And the volume that we're grabbing is actually just the volume of a perfect box. And so here, our net volume here is length times width times height. And so we can grab our length and width from our description of the rectangle. The x direction going from -2 to 2. And so it's a stretch of 4, and in the y's we're going from 1 to 6, so that's a stretch of 5. And so length times width, we're getting 4 times 5, and then the height, we're just going up to our graph at z equals 3. So multiplying those together, 60 units cubed is the exact value of our double integral here. Moving on down. Now we're doing some estimating. So we have a function given to us here. So here's our f of x, y. We have a particular rectangle over here, and we're going to Riemann sum using this particular grid. And a couple of different ways we can get evaluation points. So let's get a graph of our rectangle to start. And so our rectangle, draw a big graph here. The x's moves from 1 to 2. And in the y's moves from 0 to 3. And so here we go. X's from 1 to 2, y's from 0 to 3. So here is our, that last one was supposed to be on the x-axis. Here's our rectangle R. So we're grabbing net volume given by our green function over top. Right? We can't see it. It's just a two-dimensional domain picture. We're grabbing net volume over or under this thing. All right. So looking at our grid here, m being 2 is telling us that moving in the x direction, we're seeing 2 boxes, and so we should cut down the middle. And similarly, the n being 2 is telling us that moving in the y direction, we are seeing 2 boxes as well, so we'll want to cut right in the middle at 1.5 as well. And so here is our grid. We got our 4 subrectangles. Now our evaluation points for the first part come from the lower left corners. So in this first box here, we're going to the lower left. That's our first evaluation point. And our second rectangle, go to the lower left. And similarly, third rectangle, go to the lower left. And for our fourth, we'll go to the lower left. And we get our 4 evaluation points for part A. And so here we go, our estimate for the double integral of our function, I guess 1 plus x squared plus 3y, then just adding up the different volumes of our 4 skyscrapers that we get over these rectangles. Yeah, and so we're going to have on the top left, we're going to have f of our evaluation point, which I guess is 1, 1.5 times the area of that subrectangle, plus a similar expression for our second subrectangle. So the evaluation point is 1.5, 1.5 times our delta A. And for our third rectangle, evaluation point is 1, 0, and the last one is 1.5, 0. All right, so here's us adding up the volumes of our skyscrapers, and we can actually pull out our delta A, and maybe while we do that, let's actually figure out what it is. Delta A here, if we want, we can get by taking the area of our rectangle, dividing it by our 4 subrectangles. So area of A divided by 4. So what do we get? Area of A is 1 times 3. Divided by 4, which is 3/4. So we're pulling out our delta A 3/4, and then we have our 4 function values to compute. This is probably where we might bust out a calculator. I think let me do the bottom ones. I think we can do those by hand. All right, so over here, f of 1, 0, we plug 1, 0 into our function, y will 0 out and get 1 plus 1, so we'll get plus 2 there, and then if we plug in 1.5, 0 into our function, and the y part goes away, so we get 1 plus 1.5 squared. And similarly, we'll get our get a function value when we plug 1 and 1.5 in to our function, and similarly when we plug 1.5 and 1.5 in. I'll let you crank through that, and just we can use our calculator to put all that together for us. What we get at the end of the day is 117/8, which actually is decimal approximation is dead on equal to 14.625. All right, for part B, we're keeping the exact same rectangle, but different evaluation points. Now we're using the midpoints. And so over here, in our first rectangle, instead of going to the lower left, we're going to go right in the middle, right here. And in our second rectangle, we're going to stay right in the middle. Third rectangle, right in the middle. Fourth rectangle, right in the middle. So these will be our 4 evaluation points. And so similarly, our double integral for our function f over this rectangle. Now we're going to approximate. Again, we're still adding up with volumes over each of these subrectangles. We just have different evaluation points. So for the first rectangle, what's this going to be? Looks like 1.5 was halfway, and so I guess this is 1.25, and this over here would be 1.75, and then let's see, this cut here was at 1.5, so that means halfway up, it's 0.75, and so this is going to be at what, 2.25, 2.25 there, and then 0.75 for those two. Okay, so our first evaluation point here is 1.25. Y value is 2.25. And then times our delta A, right? And then our next evaluation point is 1.75, 2.25 times delta A. Then our evaluation points below, f of 1.25, 0.75 delta A. Then our last evaluation point is 1.75, 0.75 times delta A. I'm going to scroll down just a little bit, and so as I say that, I'll wait here. Just, once again, we can pull out our delta A. It's still 3/4, right? We have the same rectangles, but now we'll just have our 4 function values to crank out using our calculator, plugging each of these x and y's into our function. I'll let you work through that. At the end of the day, plugging those in, adding them up, multiplying by our delta A gives us 375 over 16, or in decimal, it's equal to 23.4375. All right, next, looking at Colorado. So we have a contour map, and we're wanting to use the midpoint rule to estimate the average temperature. And so here we're going to use our two-dimensional formula for the average value of a function. The idea here is we're adding up all of our information with our second double integral, and then dividing by how much information is there, the area of our region here, our lovely state. And so here, if we're going to use the midpoint rule, then we are looking at estimating this double integral. All right, so we got to get that going, but maybe first let's figure out the area of our rectangle. So the area of our rectangle is this length times width, and so here we're given those 388 and 276 miles. So 388 times 276, and that works out to be 107,088 square miles. And all right, so now if we're going to estimate our double integral, right? Then we just need our grid, and that's handed to us here. And so 4 and 4, so moving across in the x direction or the y direction, and we're moving through 4 boxes, moving in the x or the y. And so here we can kind of eyeball things, cut in half, then cut in half again, and cut in half again. And so here are our subrectangles. And now we just need to figure out the midpoints of each, and I'll use the very accurate method of eyeballing them. To get our midpoints going on here. And so here, from our contour plot, we can get an estimate as to the values of our function, the temperature, at each of these points. Here we're just kind of doing our best estimating with the information available to us. Right, and these will be giving us our function values that we'll use as part of our formula. All right, so let's see. Our double integral, right, over a rectangle of our temperature function. We'll say it t of xy. Okay. We're estimating that by adding up all of our function values. Let me say it like this, right? It's the double sum of our function values times our area of our subrectangles, the delta A. And so we can figure out delta A, right? So that's going to be our area divided by 16, since we have 16 subrectangles, and that's 6693. It's the area of each of our subrectangles. And we can actually, now, as we did before, that's going to be a common factor in each part, and so we'll just pull that out and just work through this. We're just going to add up our function values, and so I'm going to say this is maybe a little bit bigger than 28. I'm going to say 29 plus maybe a little bit less than 24. Let's say 23 plus maybe a little bit bigger than 44. Less than, I think less than 44. I want to say 43. 43 plus 43. Then over here, I think we got to go by the color. It looks like about something similar. Say 44 plus, I'm going to say 16 there. 32 for this rectangle here. Moving over here, let's just call that one 48. Next, looks like it's on the line. Looks like yellow to green, or let's say that's 44. Right on the green, I think that looks like, what is it? 28? And so on. This is how it's going to go. If you want to stick with me for another minute, we'll get there. It's a little bit bigger than 56. I'm going to say 57. Over here, green to yellow, 44. And then, again, green to a little bit darker green, 28. Plus middle of green, let's say, I don't know, 30. Orange, let's say 54. And then the very last one between 40 and 44, let's say 42. And if we crank all this out using a calculator that I'm trying to find, oh, here it is. Great. What do we get? 29 plus 23 plus 43 plus 43. By the way, if you estimated your function values slightly differently than I did, then you should be ashamed of yourself. I'm just kidding. That's totally fine. As you could tell, I was just totally eyeballing and just getting some rough estimates. All right. With my estimates here for the stuff in parentheses, I'm getting 605. When I add that all up, putting that together, getting 4,049,265 for the approximation to our double integral. And so our average temp, right, which is our double integral over the area of our rectangle, would be that 4 million-ish divided by our area, 107,088. And so it's dividing those two numbers. We get about 37.8 degrees Fahrenheit as the average temperature at that time. All right. Good work, everyone. I'll see you later.